Hello, everyone, and welcome to this presentation on computational design for thermal application. This presentation will be showed at all events during Formnext, yeah, I'm happy to be your presenter today. My name is Guenael Morvan. I'm a senior application engineer at nTop. Yes, and today we're going to talk about computational design and thermal applications. So first off, what is gonna be what we're going to see today. At first, an intro on computational design, and after that, we will see a bit more like what nTop can provide in terms of modeling with our kernel implicit modeling, and what kind of a thermal feature you can expect to do in nTop. And finally, we will go to a quick study on parameterization and design studies for thermal application and how we can leverage computational design for this kind of studies. So first off, what is computational design? It really enables you to iterate and mostly to get better performances. So when we see traditional design, it's a lot of iteration and cumbersome design work to redesign the part after meshing, simulating, and so on. So we iterate, and it's a bit of a slow process. In that case, very simplified in the slide, but it's kind of cumbersome and doesn't allow you to be quick in finding the right design. So computational design process enables you to, at least in nTop, to build a computational model. So that means like we have a set of input of parameter, and we encode the design logic to get an output, or multiple output, could be two. After that, we run the computational model. So that means that it runs automatically to get like a lot of different iteration on the design and to enable you to find the right design, the optimal design for your application. We can then integrate, validate, and go to production with the optimal design. So that's how computational design process is built in nTop. And yeah, how we can basically leverage implicit modeling to get to the right design via a lot of different way of automating the process. When it comes to design iteration, it's not always very fast. So we do like one design number one, then we go to design number two, etc. And it takes quite a lot of time to do that. And it's a lot of manual process to get to that result and end up in a lot of design work and time to get the optimal design. So that's with traditional processes, basically. But here, with computational design in nTop, it really shows that it might take a bit more time to build up your process, to build it up, to parameterize everything. But then, in the end, it will end up in a lot of in a better way to iterate, to get to the right iteration by just like automating the full process. And that gives you at the end the optimal design that is done, that is optimal for your application. And this all design iteration work is a lot more optimal than with traditional tools. So that's how you get better results basically in less time. nTop is really the tool that is built for computational design. So that means that nTop is using first the implicit modeling kernel, and that gives you the power to create complex geometry, but also to parameterize everything. To be able to run this computational design, we have different ways, but the most efficient will be our nTop automate that is running without the GUI, and enables you to run all the iteration at once. And we will see later on an example that shows like how nTop can be used in design of experiment or any type of design studies. And finally, the ultimate step is to integrate, to validate, and to go to production. And for that, we have nTop Core that enables you to export your design, but also integrate with different CAD CAM simulation software. Now let's go to thermal applications. Implicit modeling enables you to create a lot of different type of things. So meaning like for thermal application, maybe for more traditional type of heat exchanger or heat sink, we're gonna see like different type of pins. We can also use data to orientate, for instance, like pins on the right side video. You will see pins that are oriented based on the velocity field of that simulation, and this data can come from anywhere. But we see more example on that. Another thing that is more advanced, let's say, will be like more the use of like TPMS part. So with different cell size, wall thickness, and so on. With varied periodicity, so being able to increase the length of the cell size to reduce, for instance, like pressure drop, or getting actually data from the CFD to change these parameters. But also like tailored path TPMS, so meaning like when you want to warp a TPMS, either gyroid or diamond cell, onto a complex path that can be also done in nTop. And this is all powered basically by implicit modeling. There are also like some more like experimental thermal features that we see and that our customer can explore. This could be, for instance, tapered base fin, or maybe perforation or emboss to create some disturbance in the flow. That can be quite interesting when it comes to CFD applications, or maybe like a full tailored surface based on the customer requirement and what they want to do with their application. We also have the ability to use what we call field-driven design for different thermal features. So what is field-driven design? You could also call it like a data-driven design. So that means like using some data, using some fields to change a design and to apply a design rule. And I think that's where nTop comes in very handy to be able to link simulation to design itself, and use this simulation results to actually change the design. For example, here on the right side video, you will see that we have a temperature point map that is defining how many pins we have. So that means, for instance, like where we have a higher temperature, we want to have more pins. So we are going to increase the number of pins in this. And that can be one design rule that is set up in nTop. Design rules is up to the engineer to decide, and it's all part of this in the computational model to be able to set up like the input parameter, etc. And these design rules can be applied to the design afterwards. So here we are changing the number of pins that we want, but we could also be changing the thickness of the pin, or any type of a design feature that you think that we think can be changed and optimized in nTop, can be done via field-driven design, so using data to drive this design. And this is fully like a automated process when it comes to linking these design features with data. And that's how we can also do it on a bigger scale. So that means like, for example, for this full heat exchanger, that is also available on our website if you want to have a look. But basically, we start with a design, we go to the CFD tool together with nTop, and we iterate up to the point where we find the optimal design with the right pressure drop, with the right inlet-outlet temperature, etc. So that's the way that nTop can be used for, in that case, this two-fluid heat exchanger. Now come the design parameters and DOE automation. So nTop can be used as as a tool to automate, to do this type of design studies. And that can be quite interesting to understand what parameter is affecting the design. For instance, the first step will be to the automation is to determine the design parameter. So in that case, let's say we are going to change the lattice type as well as the number of unit cell. So meaning like increasing the unit cell. The aspect ratio. So here we are stretching the gyroid in the flow direction. And the mid-surface offset that is changing. So the mid-surface offset enables you to get one fluid domain that is bigger or smaller than the other one. So that's another feature that you can do in nTop. From this, we are going to set up a design of experiment. There are multiple ways to set up a design of experiment. In that case, it was done through a table. It can also be done via nTop Automate using a Python script or any type of a script. And this design of experiment set up like for each of the variable that we had before, right? So we are going to have one iteration. And after setting up this design of experiment and the workflow in nTop, we can get for each iteration one mesh or one output that we are going to export from nTop. So that's going to be the output. So we have input on top of the screen here, and then we have the output that will be the geometry. So for that, the workflow is set up in this way. So again, we have few input, but also like the output. The output here is a CFD mesh that is directly exported with the CFD boundaries on the mesh itself, and we'll be able to import it later on into a CFD solver. All the outputs are generated via the design of experiment, as we mentioned before. And so these are like the input, the workflow, and then the output here in red. And via the automation, we get all the design set up and exported as a .msh file in that case, as we are going to import it into a NSYS discovery afterwards. So here we see like for each iteration, we get one mesh. After we have all this mesh, they need to be transported or to be automated into the CFD solver. So for that, it's a step that is outside of nTop, but thanks to the way that we can export the mesh with a .msh file, this can be done automatically using like for example a Python script or using a script in NSYS. And this will be the input variable that we have. So water, so constant flow rate, pressure outlet, fidelity set to the highest. And then the output variable, so what we're interested in. So in that case, the velocity streamline, so as a PNG file, the pressure differential as CSV, and the maximum velocity as CSV as well. And after automation, we get the results and all the CFD file, the PNG file, etc., that are exported. So again, another way of like automate it from nTop and to integrate into a CFD solver, in that case, NSYS discovery. So after that, we can analyze all the results, of course, in which we are going to get a lot of different design. For each design, there are like different results, but we can see for each design like what is maybe the right design for the application, but also not only that, we are getting like a lot of information on the parameter itself. So what is the parameter that is affecting the output? So meaning like what parameter is affecting more the pressure, etc., etc. And there is more to see also on our learning center on these full studies. So if you are a customer of nTop, you can access our learning center and see how this whole design was set up, get access to the nTop file, and see also all the results. So I do encourage you to have a look at that if you haven't done it yet. And yeah, that's a great study that really shows like how you can leverage nTop automation to get all this data and to analyze them and to see what parameter and so on. nTop is also like sometimes used as a geometry creation to get like this type of data to automate this process of of to this process of like having like all this output data in the end. And some of our customers, they like to use it also to feed it into a machine learning to actually predict what type of outputs will be with which input. So that can be also a good way to leverage nTop in machine learning workflows. So thank you everyone for for your attention. If you have any question, don't hesitate to come at our booth. You can also contact us at sales@ntop.com. And if you want to learn more, go to our website. There are a lot of case studies there. Thank you very much.